All right. I have, for the record, Michaela and Christina here. There's Michaela. And notice I changed the title here to say centripetal acceleration. And yeah, I left the picture for the force. We're going to finish up just a few things on how to use Newton's laws and then move into centripetal acceleration, which is another place where we're going to apply Newton's second law, or well, Newton's laws. So, starting right in with a clicker question. You are in an elevator that is accelerating downward at 2 meters per second. What do you weigh? So one of these forces is the force you weigh. I only have 7 people who've answered here. Well, got to move on. I apparently messed up something also with the clicker IDs. Who has clicker 6676D? It would be Tyler, Andrew, Colby, Joseph, or Denver. That's yours, Joe?
Yeah.
Okay.
Channel 33.
Channel 33, yeah. Yeah, people I named are the ones who I don't have answers from, in case you're... I know I had Joseph registered before, but I tried to update things, and apparently when I updated, it set you back to, well, it set you to 6F29E. Okay, now we have, it still shows you haven't answered, Tyler.
It's coming up in number. It's not giving me the number.
Because it gives you an option to put more than one.
Oh, okay.
My bad.
Thanks. Yeah, they don't want people to miss out. Okay, so, yes, everyone that's here is answered now. All right, so the answers we got were 1, 6, 4, and 0. I probably should have made it only 1, but there are 2 answers that you could reasonably have argued. And they're the 2 answers that garnered the most points, or the most clicks. One person said force of acceleration. 2 people for their potential test question from Monday had as a question, which is not a force, and force of acceleration was one of, a correct answer for not a force. There is no force of acceleration. How are force and acceleration related? A force causes an acceleration, but there is not a force of acceleration. There are forces like, this is pushing or this is pulling, and the acceleration is a result of that force. You don't have something accelerate and thus cause a force. Now you can have a collision, and then it's a contact force. Okay, and of course force of friction, we haven't studied it yet, so that wasn't the answer. So these are the 2 you could have answered or could have argued. What's the argument in favor of the force of gravity? Why would you say the force of gravity is your weight? 4 people said that. Okay, because your weight is the force that the earth is pulling down on you. That's a common definition of weight. And so it would be a fair answer for you to say, well, it's the force of gravity because that's the force that the earth is pulling me down with. So that's a fair answer. The other fair answer is the normal force. Why would the normal force also be a fair answer?
It's the force that's holding you up.
It's the force that's holding you up. If you step on a scale, the scale measures the force that's holding you up. And so that's what we measure when we measure our weight. So you can see how both of those would make some sense in terms of what we colloquially call our weight. Given those two, if you have an astronaut in the International Space Station, like I talked about on Monday, if we say that astronaut is weightless, which one of those two definitions are we using? Not the force of gravity, because the force of gravity there is still 80-90% of what it is when you're on the surface of the Earth. But their chamber is falling with them, so that's the definition that you would use, the force normal, to say an astronaut is weightless. Obviously, in space, is weightless. The force of gravity is the one we would use to say, no, he's still, every bit as heavy as he was there. Now, just a couple funny stories. Astronauts, when they go into space, they weigh them. Well, you can't weigh them. You can't have them stand on a scale. There's actually technically a different term. They measure the mass of the astronauts. They measure the mass by having them sit in a sled that has springs attached, and then they go back and forth, and the frequency tells them what the person's weight is. If you have something heavier, it's going to take longer to go back and forth. Something lighter goes faster. So they measure the mass. Why do you suppose they really care to measure the mass of the astronauts day after day in space?
Make sure to stay healthy.
Yeah, they want to stay healthy. Here are some things that happen when you go into space. Thing number one that happens when you go into space is you get taller. Why would you get taller? Because not so much the gravity, but the weightlessness. Right? You're weightless because you're in a chamber that's falling the same rate as you are, and so there's nothing compressing you. Right now, gravity's compressing my back. So when you got up in the morning, you were at your tallest. And throughout the day, you're going to shrink maybe as much as 3/4 of an inch to an inch. Throughout the day, you're going to shrink because your back is slowly being compressed. Well, the astronauts aren't having that slow compression, and so for them, their back just reaches this nice equilibrium length, and they might grow 2 inches while they're in space. Now, of course, when they come back to Earth, like an accordion, they crumple back down to their original height. But they get taller, which is cool. Right? I'd like to... 6'5" was my goal. Although, when I started high school, my goal was to be 5'9". I thought that would be so cool if I could get that tall. But anyway, I grew past 5'9". When I set my next goal, 6 foot. Hit that. 6'2". Hit that. 6'5". Okay, so they grow taller. Their muscles and their bones both start deteriorating for the same reason. Why would their muscles start deteriorating? Yeah, they don't have to do much that involves strength. Now, if you have a refrigerator and you want to move the refrigerator, what's the first thing you have to do? To make something move, you have to apply a force. And the acceleration is going to be that force you apply divided by the mass. So if you have a refrigerator in your space and you want to move it, you've got to apply a force to get it moving. And as soon as you have it moving just like an inch per second, probably be best to stand back. Let it go where you want to go, and then over there apply a force to stop it. So you do have to apply a force to start and stop moving things. But you can sit there and hold the refrigerator all day long, and it wouldn't tire you out because there's no gravity, net gravity, for you to worry about. So that's why their muscles start atrophying. They don't need them. So they have gym equipment for them to exercise to try to keep their muscles from deteriorating. Their bones atrophy, or actually leach calcium out of them for basically the same reason. God designed us so that our bones will grow in strength, building more bone density, if we are using them, if we're putting compressions on them. And so if they're not putting compression on the bones, the calcium levels drop by actually a precipitous amount. So when they come back to Earth, they're at risk of breaking a bone pretty easily because the bones have become much weaker while they're in space. And so how do you fix that? Well, you've got to put some load on the bones to try to keep them from weakening more than necessary. So once again, the exercise equipment is a way to put some load on it. A final thing that you may not have thought about is your sense of balance. We can probably all stand on one foot, close our eyes, go like this, but we're going to wiggle around, right? If I open my eyes, I do a better job. I don't wiggle around as much because I have the reference of seeing everything and not just relying on my body's feeling. So I can balance like this. You take an astronaut who just came back from space? Nope. Why not? Because your reflexes to correct your balance start wearing away when you don't need them. And so they're in space and they don't need to balance, and nothing is maintained. And so they actually will have like a board or something that they push on their feet. I've read that when they sleep, they push on their feet. So that you have that pressure on there, and you maintain some of that reflex to keep you balanced. Pretty weird stuff, isn't it? Now, what does that have to do with our topic of the day? A little bit. I talked about astronauts' weight in space, but it's all related to physics. Oh, one last thing. The weight in space. One of my friends in graduate school, his uncle was an astronaut. And he was one of very few astronauts to gain weight in space. And the reason is kind of rude. Defecating in space is unpleasant. You do your business and then you use a spatula to clean yourself up, and I think then a wet wipe or something like that. And so nobody likes to defecate in space, and what's the best way to avoid defecation? Not eating food. And so there's just a natural, not conscious, but subconscious tendency for the astronauts to eat less so they don't have to poop as much and go through that process. So, yeah, that's why I really started on that, was to get to the whole weight and mass thing in space. I spent 15 minutes on that. Question number 2. A ball hangs from a string attached to the ceiling, kind of like I have set up here. What direction is the net force acting on the ball? Okay, let's see. Denver, there we go. So we have some variation here. So turn to your nearest pal and discuss with them what your answer is and how you came up with it. If you're the same, try to find somebody else who is different. If you're different, try to consider reasons. Do you guys all agree?
Yes.
Well, that's all but one then said that answer.
Yeah, I think it's.
Did you convince them, Daisy?
Yes.
Good. Now let's see if you convinced them correctly. So let's answer again. I already have one more correct answer than we had the first time. Ah, boo. One person was correctly switched. Well, it worked for one person. Okay, the correct answer was 0. Since I know this group of 3 all agreed on 0, that's why I was like, oh no, this isn't going to work out. Only one person outside that group answered correctly the first time. Okay, and that person must have convinced at least one other. So you people in this group, why is the correct answer 0?
Because if there's a force acting on it, it would be accelerating.
Right. If the net force wasn't 0, its velocity would be changing. Right now, its velocity is constant. What's the value of velocity? 0. Right. So right now, the velocity is constant, no acceleration, hence the net force is 0. Why did 4 people answer downward? I'm right. It's not an illogical answer. Why did they answer downward? I know the reason. It's not like it's yeah, because gravity's acting downward. You're like, well, of course, it's just got gravity acting on it. If it wasn't tied to that rope, that'd be correct. It would be a net force downward. But that rope, or in this case, the cable, is applying a that's the second time I've done that today. An upward force so that the net force is 0. That force we call the force of tension. So if I draw the forces on this, really? It's become non-sensitive to my finger again. I have the force of tension going up and the force of gravity going down. So let's talk a little bit about this tension. It's a new force to you, right? I haven't said tension before. Tension is a force that is transmitted through something like a string. You can't compress it. You can only put it in tension, right? I can't take the string and put it up against this surface and then go, huh, and move the surface. It's not going to do that. But if I had it glued to a surface and went this way, I could pull it. So tension is only pulling something tight, not going to allow you to push. But of course, anything that pushes or pulls is a force, so that pulling action means that there's a force involved. Now what the tension does in an ideal rope or string, I have to identify ideal. Ideal means it has no mass and doesn't stretch. This string obviously has some mass, and it does stretch a little. So it's non-ideal, but for physics purposes, we'll just talk about ideal. So in an ideal string or rope, the tension is the same everywhere in the string, and it applies the force to anything that the string is touching. And that force is equal to the tension in the direction the string is leaving. So if I look at this, I had some tension that I'll call T that was in that string, or cable, whatever it was. And where it attached to the mass, what direction was the string leaving the mass? Up. And so it applied a force that was upward with the magnitude of the force equal to the tension. Now if we look at that ceiling, if you will, that's what it's supposed to be, the line of dashes. What direction is the string leaving the ceiling? Down. So what does that tell you about the force the string is putting on the ceiling? It's pulling down. Now let's go a step further. Later on I'm going to have a picture with a pulley. Let's say I have a pulley here, and I have a string that goes like this. So I have a mass hanging here. Here's the wall. Is that a question? No, it was the answer to the anticipated question. Okay, let's start with a simple question relating to this picture. And that simple question relating to the picture is, what is the tension in the string? Now, I put M here. Let's specify M is equal to, since I heard 2, I'm going to put 2 kilograms. If M is 2 kilograms, what is the tension in the string?
Well, hold on. Depends on where the
if I'm going to find the tension, I need to know what a force is on the string, right? And so I look at the string. How many places is the string leading things? Actually, not twice. 4 times. It leaves the wall, and then it comes to the top of the pulley, so it's leaving the top of the pulley. Then it leaves the pulley on the side, so that's a third, and then it's tied to the mass. Now, with those 4 places where it's attached to something, which one can I make some statement about other forces involved?
The ones at the pulley.
Not at the pulley. I appreciate that you're answering. Don't.
Taking away from the wall. Pulling.
Not there either. That gets us to the answer. What's the one remaining? At the mass. At the mass, I can look at this and say, just like in my picture I drew over there, the forces on that mass are an upward force of tension that has to be equal magnitude to the tension in the string. And the other one is going to be the downward force of gravity that's equal to mg. Now, if it's just sitting there stationary, then what do you know about those forces? They're what? I believe he said they're equal. Because the acceleration is 0, sum of the forces is equal to mass times acceleration. So if I just look in the vertical direction here, I'll consider up positive. The sum of the forces would be force of tension minus force of gravity equals mass times 0. Which then gives me the answer for what the tension is. Force of tension is equal to the force of gravity, substituting that tension is T and force of gravity is mg. Remember, g is always going to be 9.80 meters per second squared unless the problem tells you to use something differently. So the tension is 19.6 newtons. Does everybody understand how I got that tension? I had to apply Newton's second law to something where I knew something about it. I knew one of the forces, and there were 2 forces, and I knew the acceleration. So knowing the acceleration of one of those forces, I could find the other one using Newton's second law. Now that I have done that, I can come back and I can answer other questions like, how big, that's not the color I wanted, how big is the force of the string pulling on this wall? The same tension, because the tension is the same throughout the string. What does a pulley do? It only changes the direction. It doesn't affect the tension. Now, if I tie something to the string, that's going to change things. But a pulley, it just changes the direction. An ideal pulley. Ideal pulleys have no mass, by the way. And there's perfectly no friction. They rotate freely. So I'm going to have a force of tension here that's equal to that same tension of 19.6 newtons. Now the tougher question. What force does the string put on the pulley? How many places does the string leave the pulley? 2. And we said that it applies a force equal to, what's the magnitude? The tension. And what about how do we determine the direction? The force of tension has a magnitude equal to tension and a direction of the direction the string is leaving. So if I look at the pulley, I'm going to have 2 forces from tension, one like that and one like that. And so the force string is putting on the pulley is going to be the sum of those two forces. So if I look at the sum of those two forces, I had one like this that was 19.6 newtons, and one like this that's 19.6 newtons. How can I find the resultant? That's what we call the result when we add these up. How can I find this force total acting on the pulley? I was asking you to go back to, my son's a sophomore in high school, and this is what he's been studying recently. So hopefully something you learned in high school. That's right. The Pythagorean theorem. Right. The reason we have the math requirement for this class is because you're expected to know this kind of thing. And if you don't, well, it's something to brush up on. So the F total is the square root of 19.6 newtons squared plus 19.6 newtons squared. Pythagorean theorem is a squared plus b squared equals c squared, where c squared is the hypotenuse of a right triangle. I suppose you don't have to say of a right triangle because there's no side you call the hypotenuse if it's not a right triangle. But so doing that, F total was the hypotenuse. Do the math. It's just going to be 19.6 newtons times the square root of 2 times 1.41 if you prefer. Going to leave that instead of actually calculating a number. So on this slide, besides just having a clicker question, I did a fair amount of work dealing with a new force. What's that new force? Tension. And tension, what does tension actually do? Okay. Being technical, the tension is distributing a force from point A to point B, or making the force that's over here act on this object. And it can only work pulling, can't work pushing. And so we have a force, the magnitude is equal to the tension. That's what we call the tension, is the magnitude of the force it's going to apply. What's the direction of the force applied by a tension? In the direction, can you say louder, Denver? Away from the object in the direction that the string is leaving. So always in the direction the string is leaving. And I think most people tend to be a little surprised when they see that the force of tension is pulling the pulley those two directions, and yet they're not surprised at all because they know that you have to push the pulley up like that. You have to have a force of support up like that to keep it in place, or it's just going to fall. Why does it have to be off to the side? Because the tension was pulling it in. And, of course, up because tension was pulling down. Okay, any questions on this? It was a new force, a new idea. Don't see any questions, so I am going to move to my next slide, which has to do with the ideas that we just learned. Now, don't answer yet. And now I hit it too many times. Okay, now you can answer. Two masses connected by string are placed on a fixed frictionless pulley. It's an ideal pulley. If M2 is larger than M1, will the two masses accelerate? Okay, every single person said yes. And they are correct. Based on what we just learned, we know there's going to be a tension in the string tying the two together. And we know that each mass is going to have a force due to gravity. So if I look at the picture, since it says that M2 is larger than M1, then if I draw the forces, force gravity 2, force gravity 1, I drew the lengths with comparison to each other, how do those two forces relate? How do they interact?
The heavier one will pull up the less.
Okay, the heavier one is going to pull up the lighter one because they're connected with that string that's transmitting the force from one to the other. So I can look at this, and for each one of these, I can put the forces. So I'm going to have an upward force here, that's force of tension, an upward force there, that's force of tension. Agreed? How do I figure out what the acceleration is going to be for something like this?
You need to know how much the mass is.
Okay, I'm going to need to know the masses if I'm going to get a number. So let's say mass 1 is equal to 1 kilogram and mass 2 is equal to 2 kilograms because I won't forget those numbers. So I have numbers now. Same question, how do I find the acceleration? Okay? Take the difference of the two. That is correct, but I want to show the work to get there. So the work to get there is going to be applying Newton's second law to each one of these. So first I'll apply Newton's second law to this. And so I will put for that one, oops, the sum of the forces on object 1 is equal to mass of object 1 times acceleration of object 1. Looking at my picture, once again considering up positive, what do I get for the sum of the forces on that object? And I've done this enough times, I actually want you guys to tell me the answers. I don't want to jump in myself. I'll start with a leader question. How many forces are acting on mass 1? Okay, we have 2. And then for the sum of the forces, I'm adding those up. So I know I'm going to have those 2 forces. Which one is positive? The one going up. So I look here and I say, Ft was going up, so that's going to be a positive Ft. One of them was going down. Which one was that? Fg1. So I put minus Fg1 because it was going down is equal to M1A1. Now I'm going to substitute for force of tension. I'm just going to put tension because the magnitude of the force of tension is the tension. And for the force of gravity one, I'm going to put M1G because we know force of gravity is mg. So there I have my equation for box 1. Now that equation has 2 things I don't know, the tension and the acceleration. So now I have to go to the second box. I have to first move it and make the second box. So here's my second box. And I'm going to apply Newton's second law on that one as well. So what does Newton's second law tell me for the second box? I wrote Newton's second law. I just replaced ones with twos. What do I have for the sum of the forces? Okay, now the tensions are the same because it's the same rope. So I just put Ft for that. But then minus Fg2 equals M2A2. Making the same substitutions as I did before. Tension minus M2G equals M2A2. Now I have 2 equations, and I have those 2 unknowns, tension and acceleration. But I have A1 and A2, so technically that's 3 unknowns. But there's a relationship between the acceleration of number 1 and the acceleration of number 2. And what would that be? Yeah, they have to be the same magnitude because one side goes up, the other one goes down the same amount, but they're opposite directions because up versus down. So I will simply assign then, based on that statement, a third equation of A2 equals minus A1. And so this will become equals minus M2A1. Now I've got two equations with just two unknowns. And to solve, to find the acceleration, I would, well, here's what I would do. There are lots of ways you can do something like this. Hey, it's back to working, my fingers. I don't understand why it loses and gains it. I'm going to write one on top of the other. So I'm going to put tension minus M1G equals M1A. The other equation was, tension minus M2G equals minus M2A. I just wrote A instead of A1 because now I only have one acceleration. And I'm going to subtract these. I'm going to subtract one equation from the other. Not subtract, add. If I subtract them, I'm going to have the... Oh, no, I'm right. I am going to subtract them. I want the tension to disappear. Subtract them because then I have tension minus tension is equal to no tension. So I have tension minus M1G plus M2G equals M1A plus M2A. Notice on the bottom, because of the subtraction, I had to change all the signs. The right-hand side, I can factor out the M1 plus M2. These here add out to 0, and I'm left with A times M1 plus M2 is equal to G times M2 minus M1. There you get the difference that was mentioned by Tyler. Get A by itself. And I now have my final answer. The acceleration is equal to G times the difference in the masses divided by the sum of the masses. Why the difference in the masses? Because the difference in the two forces is G times the difference in the masses. Why divide by the sum of the masses? Well, because acceleration is net force divided by the total mass. And so the sum of the masses was the total mass. So this was not as simple as what we've done before, right? Things get a little more complicated, but in the global scheme of things, very doable. I saw you taking pictures. Remember, these slides are available on Moodle, so you can just go look at them there as well. Okay, a reminder of Newton's third law. Newton's third law, for every action, there's an equal and opposite reaction. The next slide says exactly that. It is most useful, of course, when we're considering two things that interact with each other. Now, let me take an example. I'll go to the next slide. I don't have anything really to talk about on that one. The action and reaction idea. We've seen a lot of movies, probably. And in movies, you have people who do things like they're fighting and they headbutt somebody. Every now and then, they're realistic on what really happens there. When you headbutt somebody, and since you're in the front row, you're my example. I come up to Tyler, I grab him, and bam! I whack my head, and you notice we didn't come very close at all because I don't want to hurt myself, much less him. We bang our heads against each other. I put a big old force from my forehead onto his forehead. If I put a big old force that went from my forehead onto his forehead, according to Newton's third law, did he do anything to me?
Yes.
Yes. How did the force of his forehead pushing on mine compare to the force of my forehead pushing on his? They're equal. So if I bang his head and really scramble his brain, I'm not going to be doing so much good for my own brain, right? My headbutts are stupid. Yeah, I say they're stupid, there are ways that you can be the winner in a headbutt. First of all, what causes the biggest problem with the brain injuries is the counter-coup action. My nephew, 14-year-old freshman in high school, he's playing freshman football this year. He's a big dude, which is funny because his mom and dad are short. Anyway, he's like me in every way, pretty much. Except for he scored a perfect score on his exams, whereas I never did that. You know, the like Iowa test we take. Anyway, so he's playing offensive line, and he tries to hit a defensive lineman, kind of misses, and they end up having a head-to-head, helmet-to-helmet collision. And while both of them were concussed, he played the rest of the game. His teammates were yelling because he was like forgetting what he was doing, making the wrong things all the time. Coaches didn't realize what was going on. Afterward, they sent him to the hospital. And he's all like, I got hit here, but it hurts more here. Why? Because he wasn't ready for that helmet-to-helmet collision. He didn't expect his head to get hit. His head was just up there hanging around. And so when it hit, and the head goes banging this way, and then the head stops, and the brain inside goes and hits the other side of the soul. And that's the counter-coup action. He was not able to go to school for the next 2 months because of that concussion. And he is just now getting to where he's able to exercise again. He went undefeated the last 2 years in shot put. I'm very proud. He's able to do that again now, but he hasn't even been able to exercise up to this point just because of that head injury. So, bad idea doing this headbutt thing. But if he had been ready, if he had been expecting that, he would have had his neck muscles all tight to keep that head from, having the rocking action when he hit. And that would have minimized. So if I headbutt Tyler and he's not expecting it and I am, I can have my neck muscles all tight to keep my head from bouncing back when I hit him. His head bounces back and his brain goes boing, and it would cause more damage to him. Still ain't going to be good for me. Second thing is, this was explained to me as an Irish kiss by an Irishman. He said, like, when Americans go to Irish bar and try to pretend they're all cool, they'll come and give them an Irish kiss, which is to come and headbutt them, but in the nose. What's the difference in headbutting in the forehead and headbutting in the nose?
The nose is more crunchy.
Yes, this is crunchy. And so, the antagonist puts his forehead very hard into another person's nose, kind of crunchy, crushes their nose. The force is not as big as it would have been forehead to forehead, so it doesn't hurt the aggressor as much, except for, of course, he can have some cuts from the nose bones. But, yeah. That's another way that the headbutt can be more effective. But in the end, what's the best policy? No headbutt. For that matter, if you're going to hit somebody with your fist, which I don't recommend doing, you also don't want to hit them with your fist up here in the forehead. That bone's stronger than these bones. So you're much more likely to damage your hand than to damage their head. And they're probably going to be expecting it, and they're not going to get rocked back. So, of course, if you're punching somebody, you want to punch in a way that your hand is stronger than what you're hitting, like the mandible. That's more effective. I am not a violent person, except when I play football. When I play football, I kind of lose inhibitions that I otherwise display in life. Okay, it's important to be able to identify which force is which in a situation like shown here. I have a book sitting on a table. And so that book, of course, has a force of gravity downward that's acting on it, and a force normal upward that's acting on it. And the earth is being pulled up by the book, and the book is pressing down on the table. Now we have, by Newton's third law, for every action there's an equal and opposite reaction. There's a total of 4 forces here. There are 2 pairs of forces. The trick here is to identify which ones are actual pairs. So let me ask the traditional question. You have the force of gravity on the book. What is the reaction force to that action? what?
The natural force of the table pushing up?
That's what most of us would answer, which is why I have this question asked at that one. That's what most of us would answer, and that's incorrect. So how do we identify, wait, how do you know that's incorrect? I've answered that incorrect after I was, in my third year of physics education. It's because I didn't think it through following some organized pattern. I just looked at it and tried to, force normal is pushing up, equal and opposite to that, right? But it's equal and opposite because of Newton's second law, not because of Newton's third law. So to identify the action-reaction pairs, it has to be forces between the same two objects. So what is causing the downward force of gravity on the book? It's the Earth. It's the mass of the Earth that's pulling the book down. So that force of gravity, what they label W for weight, is the force of the Earth acting on the book. So the equal and opposite reaction force, you just have to flip those two things, the acting. So instead of the force of the Earth acting on the book, the reaction force is going to be the force of the book acting on the Earth. And so the force of the book acting on the Earth is pulling the Earth up. Now, how many people think of the book pulling up on the Earth? Nobody does. Because that's not going to make the Earth move very much. No negligible amount. When I was in college, one of my friends, she took physics at another school, and she talked about how cute her teacher was. And he said, every time you reach over to pick a flower for your girlfriend, the Earth moves. Well, it's true. A very, very minuscule amount. Because of the equal and opposite force, the force of gravity pulling you down, pulling it up. If I go down because of the force of gravity, the Earth comes up because of that same force of gravity. By a very, very tiny amount. But she just thought it was so sweet. So, how did I identify which forces were the action-reaction pairs? The ones that were directly related to each other. I often write things like force of Earth on book for this one here, and force of book on Earth for this one here. Then it becomes clear because those subscripts are just flipped over, so they are the reaction pairs. Now I think I have another clicker question. No, I have the spring part. The reason I have that there, and wow, we're not going to get to the next. Springs are another force. They supply forces. Now this spring here can only be stretched. Some springs can be stretched and compressed. And I don't have enough time to do everything I was going to do, but I can take and hang masses from here. I'm going to first hang the 20 on here. Okay, so it stretches some because I have that 20-gram mass on there. There's a force of mg pulling down. Now if I put, instead of 20, 100 grams, well, it stretches more or less, let's say. Okay? It stretches more if I put 100 grams on there. How much more? It turns out if we had the time, I would put a bunch of masses on here and measure, like a meter stick. But the amount it stretches is proportional to the force. So the force that a spring applies is some constant that we call the spring constant, multiplied by the amount the spring stretches. And if I put vector signs, I have a minus sign because the force is the opposite of the direction that it's stretched. So if I stretch that spring down, the force is going to be up. If I compressed it up, the force would be down. So the spring is a new type of force. So we have two new types of forces we talked about today. The force of tension and the force of a spring. And so now you look at this and you say, well, can't they just measure the mass of an astronaut by having him stand on a spring? No. Why not? Yeah, the spacecraft is falling at the same rate the astronaut is, so there'd be no force of gravity pulling down. On Earth, that's exactly what a scale does. A scale has a spring and measures how much that spring compresses, when you stand on it. And then it throws up some ungodly number to make you go crying home. Well, I don't go crying home. I look at it, just shake my head and call it the evil thing. So that's how we measure our weights on a scale. Now, a balance is slightly different. I think my next slide has a picture. Oh, no. I will end with this one and not talk about the balance. This here, a professor in graduate school did a great job with this. He wrote a textbook and put it in there. It's now become pretty common in textbooks. The story is that Mr. Ed, who, of course, I always called John Elway Mr. Ed because of his big teeth. Got to look at you because the NFL nixed the trade between the Colts and the Raiders that would have brought John Elway to the Raiders. And since the NFL nixed that trade, the Colts ended up making a trade with Broncos and Bronco quarterback instead. Anyway, Mr. Ed Wilbur tells Mr. Ed, the talking horse, to pull the cart. And Mr. Ed, who is a very intelligent horse, turns to Wilbur and says, "But Wilbur," in his best Mr. Ed voice, which I will stop now, "I can't possibly pull this cart because Newton's second law says the sum of the forces is mass times acceleration. But Newton's third law says for every action there's an equal and opposite reaction. So if I pull on that cart, the cart's pulling back on me with exactly the same force, so the net force is 0. And that's according to Newton's second law, the acceleration is 0, and I could not possibly move this cart, so I'm not going to try." Does that seem to make sense? Yeah, it does. It does seem to make sense a little bit. That's why we have it in the textbook, and that's why my teacher made up this question. Well, here's the flaw. Since we are now 1 minute over, I'll tell you the flaw. The flaw is Newton's second law says the sum of the forces on an object is equal to the mass of that object times its acceleration. This force here is acting on Mr. Ed. This force here is acting on the cart. They're not acting on the same object. So it's a misapplication. If you just look at the cart, the forces on the cart are going to be the force of friction and that force of him pulling. And so Mr. Ed just has to have a force bigger than the force of friction and it moves. Another way you could look at this is you could say, I'm going to make my system the entire cart and Mr. Ed. Well, then I have to introduce some more forces. There's going to be the force of friction on Mr. Ed and the force of friction on the cart. And as long as the force of friction on Mr. Ed is bigger than the force of friction on the cart, he's able to move the cart. Last statement. You guys have things like, almost anything goes, and you have a tug of war. Which team is putting, if you have two teams in a tug of war, one team wins, which one put more force on the rope?
They're equal.
Equal. Newton's third law said it's equal. Also, what a tension is said it's equal. So what decides who wins then? The one that got more friction. If you had two teams that were equal in strength, it would be really easy. One of them has like loafers with leather bottoms and one of them has trainers with rubber bottoms. The ones with the trainers win every time. Doesn't matter who's stronger. In the competitions you guys do, it probably comes down to weight more than it comes down to strength. In the games you guys play. So freshmen usually lose because they're usually lighter. We all gain weight in college. See how that works? Have a great day.